Hi, today we'll look at a pretty well-known proof on the irrationality of the number e. So let's get right to it. Recall that the function e to the x is given by this infinite series here. And to help our case, we're going to define another function, f sub n of x equals this. It looks quite similar to what we have here for e to the x. However, this is an infinite series, but this is a finite series. And when x equals 1, well, in each case we have e to the 1, or just e, the number e itself, is defined as this infinite sum. But f sub n of 1 is this, where we take x to be 1, 1 to the power k is 1, and so we have this finite series. Now take note at this stage that this function right here is actually rational. This sum is just a sum of rational numbers, a finite number of them, and any finite sum of rational numbers is rational. That's not too hard to prove, but we'll take that for granted right now. So the first thing to do is to consider the following. We're going to look at the difference between this and this. E minus f sub n of 1, well, what is that? It's this quantity here minus this quantity right here boxed in yellow. We can bring these two summations together to make it look like the following. This right here, this representation of e, we can break that up and write the sum from k equals 0 up to n. And now we still need the sum from the n plus 1th term all the way up to infinity, so we'll add that in. Minus this representation of this function f sub n of 1. But notice here that this quantity and this quantity negate each other. It's the same quantity subtract itself. So all we're left with is this right here. Now, we have this series, so let's sort of expand this out a few terms. Starting from k equals n plus 1, the first term of this series is 1 over n plus 1 factorial, plus the next term in the series gives us 1 over n plus 2 factorial, and we'll throw in one more term here, and out to infinity. Okay, great. The next move we'll pull is to factor out this quantity here, 1 over n plus 1 factorial. When we do that, what we're left with inside the brackets here is 1 plus 1 over n plus 2. Down here, this is n plus 2 times n plus 1 times n, etc. This is n plus 1 times n, etc. So the only surviving quantity is n plus 2. And from here, this is n plus 3 times n plus 2 times n plus 1, etc. And this factorial starts at n plus 1 with all numbers, natural numbers below it. So the surviving terms that are left here are n plus 2 times n plus 3. Okay, fantastic. Well, now we're going to make a comparison here to another series. Notice here that this quantity is actually less than 1 divided by n plus 1. Why is that? Well, n is a natural number. plus 2 versus n, a natural number, plus 1, this is larger than this. But since we're dealing with fractions, 1 divided by a larger number is smaller than 1 divided by a smaller number. So this fraction is less than this fraction. By a similar argument, this next term is less than 1 divided by, well, we can have a factor of n plus 1 downstairs. That smaller amount will make the fraction larger compared to this n plus 2, as well as if we have another n plus 1, that smaller quantity will outweigh this, making this whole fraction then smaller than n plus 1 squared. N plus 1 times n plus 1, and so on. Well, from what we have in brackets versus what we would have in colors here, 1 over n plus 1 plus 1 over n plus 1 squared, etc., that new series of 1 over n plus 1 factorial times 1 plus 1 over n plus 1 plus 1 over n plus 1 squared, etc. Comparing these two, this is obviously smaller because all the quantities in here, except this one, are less than the quantities in here. So we have this inequality here that tells us that this difference between e and f sub n of 1 is less than this amount here. However, what we see inside the brackets is a geometric sum. How do we know that? Well, the first term here is 1. Multiplying that by 1 over n plus 1 gives us this next term. Multiplying that by 1 over n plus 1 gives us 1 over n plus 1 squared, so that's the next term, and so on. So the common ratio is 1 over n plus 1. This is a geometric sum. So the common ratio is 1 over n plus 1. Well, the good thing about that is we can determine what the sum of all this is simply by using a neat little formula. So you might recall that the sum of a geometric series or geometric sum is simply the first term divided by 1 minus the common ratio. As long as that common ratio has a magnitude less than 1. But indeed, if our common ratio is 1 over n plus 1, n being a natural number, 1 divided by some natural number plus 1 is going to give us a fraction that lies between 0 and 1. So this common ratio is definitely between 0 and 1. So let's determine the sum of this geometric series. We'll just move up here. So we have the first term of the series, which is 1. And then we'll divide by 1 minus the common ratio of 1 over n plus 1. Well, we can fix that up a little bit. We have 1 over n plus 1 minus 1 over n plus 1. So the reciprocal of a fraction, so we'll just flip that around. 1 minus 1 cancels, leaving us with n plus 1 over n. Okay, perfect. So what we can now write is the following. This difference is less than 1 over n plus 1 factorial times what we got here as our geometric series or sum, that's n plus 1 over n. But of course, this is nothing more than, okay, we have a factorial here beginning at n plus 1. So the n plus 1 here cancels with this one here, leaving us with 1 up top. And down here, the n plus 1 goes away, but we're left with all quantities from n downward in our n factorial. So we're left with 1 over n factorial times 1 over n. Okay, perfect. So we're going to continue from here. Let's go to a new board and see what we'll do with this. Okay, so we're back. We have a list of our main summary points here, so let's continue. Let's at this point assume that the number e is rational. Well, what that implies is that e can be written as a fraction of two integers, a ratio of two integers. But since e here is positive, then we'll say e can be written as a fraction p over q, where p and q are positive integers. What we'll also do now is consider a new function similar to this here. However, our index will go up to q, up to whatever this number is here, and we'll see why soon enough. So f sub q of 1 is going to be the sum from k equals 0 to q of 1 over k factorial. Now, having done this, again, let's go back to looking at the difference e minus f sub q of 1. Well, what is this difference? First of all, it's a rational number. Now, why is that? Well, e is assumed to be rational. F sub q of 1 is just another finite sum of rational numbers, so that's rational. So rational minus rational will give us a rational number. Okay, fine. So where do we go from here? Well, using our result from down here, if we just substitute q for n's, then what we can say is e minus f sub q of 1 is less than 1 over q factorial times 1 over q. But this has to be greater than 0 because e is an infinite sum, while f sub q of 1 is a finite sum containing the same terms as e, just fewer terms. So this is larger than 0. Now what we'll do is we'll multiply through by q factorial. So we get 0 is less than q factorial times e minus f sub q of 1 is less than 1 over q. However, because q is also a natural number, 1 divided by a natural number is less than 1, unless q is 1 itself. But other than that, we now see that this quantity here is bounded by the integers 0 and 1. Okay, fine. Now what we need to do, and this is where defining this f sub q of 1 comes in handy, we're going to look at q factorial times e, and we're going to look at q factorial times f sub q of 1. Q factorial times e is nothing more than q factorial times, well, we defined e to be this ratio, p over q. But q factorial divided by q is just q minus 1 factorial. But since this is a natural number, this is an integer, this all works out to be an integer. Secondly, q factorial times f sub q of 1, what does that give us? Well, we have q factorial times, what is f sub q of 1? Let's look at some terms there. Running up to q and having x equal to 1, we essentially have this, but q's instead of n's. So f sub q of 1, some of those first two terms are 1 over 0 factorial, that's 1. Then 1 over 1 factorial, that's 1. Then 1 over 2 factorial, plus 1 over 3 factorial, all the way up to when we hit q. Well, that gives us 1 over q factorial. So except for this q over here, all these other denominators in that sum are smaller than q. But if we take q factorial and distribute it into all of these fractions, we end up with integers. Why is that? Well, remember, q is larger than any one of these denominators, except this last one. And so, for example, let's say q was 5. Then we would have 5 factorial. Distributing that to the 1 over 2 factorial, what would that leave us with? Well, the 5 factorial is just 5 times 4 times 3 times 2 times 1, and the 2 factorial is just 2 times 1. So what gets left behind is the 5 times 4 times 3, clearly an integer. And this same sort of argument holds for the other terms that we see here until we distribute this q factorial to the 1 over q factorial, which leaves us with 1. So we have 1 plus an integer plus an integer plus an integer all the way up to here plus another 1. All of this is another integer. And so what can we say about what we've arrived at here? Well, if this is an integer, q factorial times e, and this is an integer, q factorial times f sub q of 1, then we have an integer minus an integer is an integer. And so it looks something like 0 is less than some integer is less than 1. But we cannot have any integer between 0 and 1. And so our whole assumption that we started with up here falls apart, that e is rational. So the only conclusion then that this leads us to is that e is irrational. And that completes our proof. Hope you enjoyed.